So the good news with learning gluconeogenesis is there's really only one step that we really need to think about carefully because steps 1, 3, and 10 are the only ones that use different enzymes than glycolysis. And steps 1 and 3 are just basically using phosphatase enzymes to undecorate what hexokinase and PFK did. So again, we've got G6Pase and then FBPase that are doing that chemistry. So the bulk of what we need to think about doing is what happens in this down here. And if this slide doesn't look familiar because you haven't yet watched this video, I highly encourage you to do that to understand the importance of things that happen in reversing this 10th step and getting back to phosphenylpyruvate. Because once you get back to phosphenylpyruvate and you have phosphenylpyruvate in the cytosol, gluconeogenesis is pretty much a straight shot back up through glycolysis with two different phosphatase enzymes at reversing those first and third steps of glycolysis. So this video is going to focus on the chemistry details of pyruvate carboxylase and PEPCK. So first, just looking at some structural details and things that sort of happen with these two enzymes. So pyruvate going to oxaloacetate, remember we highlighted that what we're essentially going to be doing is we're going to be deprotonating that methyl group there, making it into a nucleophile, and then we're going to be using CO2 here, and I'll highlight what all these structures are in a minute, to add to this carbon. Okay, so what really happens here is we can't just grab CO2 out of the air. We don't have CO2 bubbles, right? But what we do have is bicarbonate. So highlighting a lot of what we see here with adding CO2 is because we're taking bicarbonate and we're going to attach it onto a critical B vitamin that we're going to see anytime we're doing these steps. So that B vitamin is vitamin B7, which is biotin. Here is the structure of biotin here. So biotin essentially is going to be attaching itself onto a lysine residue in the protein where it's going to be doing its chemistry, and it is a way of making what we call transferable CO2. So it's going to take bicarbonate out of just the solution that we have there, and then it's going to add it as a carboxylate group on its own sort of position here. And so it's really sitting there like it's a hot potato ready to decorate wherever you need that CO2 group to be added. So that's the chemistry that happens with pyruvate carboxylase. I want to make sure to highlight that this is not a chemistry that happens without a cost. So there is a toll booth that has to go through the toll that you have to pay there. So you do have to pay some ATP in order for this process to happen. But net is that we're going to be adding a CO2 group onto this methyl group, and that's how we generate oxaloacetate. Remembering the reason that we do this is pyruvate is an alpha keto acid. Okay, and now this gets a little bit confusing here. Just make sure we're highlighting that it's an alpha keto acid because we're referring to this carboxylate group in relationship to that carbonyl, that ketone that we have there. Now, oxaloacetate is a beta keto acid. But I want to make sure that we note that the acid part is going to be different with these two pieces. Let me choose a different color here. So when we're talking about this acid group here, so when we have this alpha keto acid, this is the acid group that we're talking about. But with a beta keto acid here, it's actually this group that we're talking about. We're not talking about the same acid group. But when we add that CO2 on, we generate a beta keto acid. So why is that important? Well, in the next step, we're going to take that CO2 off and we're going to have that nucleophile that we can do some chemistry with. Okay, so first step is using vitamin B7. Anytime we're going to be adding on CO2 to just remove it in another step, vitamin B7 is going to be essential for that biotin. So let's look at what happens in this second step now. So oxaloacetate, being that important beta keto acid, okay, is going to easily decarboxylate on its own. We're going to see in some later chemistries, just to kind of give you a little preview or review, depending on where you're at in watching this, pyruvate is an alpha keto acid. It can undergo decarboxylation chemistries, and we're going to be removing that CO2 group, but it can't operate by the same chemistry as we see with beta keto acids because we'd be putting a negative charge on a carbonyl carbon, not someplace where we could resonance stabilize that. So what we see then with beta keto acids is they easily decarboxylate, and here's the chemistry that happens, okay? don't know if I finished my thought up here. When we have pyruvate with alpha keto acid decarboxylation, we need a different B vitamin to help with that. We're going to see vitamin B1 for that. That's going to be something called TPP, thiamine pyrophosphate. So we're going to see that to help with decarboxylation of alpha keto acids. Beta keto acids do it easily on their own. Let's see if we can understand why here. Let's kind of zoom in, look at this structure. So if we zoom in here and look at this, we're going to have these electrons come down, and when we form that pi bond there is our CO2. Can't have 5 bonds to carbon, so this bond needs to break. So if we want to think about it, we can initially imagine that we just would put those electrons on that carbon. It would be very unstable if we couldn't resonance stabilize those, and it actually would be more stable to take these electrons if they were on this carbon and resonance stabilize them through this adjacent carbonyl, putting that negative charge on the more electronegative oxygen atom. What this mechanism shows, though, is all in one step, doing our decarboxylation chemistry, taking these electrons, pushing them through to form that enolate, and then having that enolate with that negative charge on the oxygen being our nucleophile to attack the gamma phosphate of our GTP here. Great leaving group in our GDP so that we can add this terminal phosphate group now to this oxygen atom, and that's how we're going to generate our phosphenylpyruvate. Let me zoom out here so we can see, again, all of that chemistry. The chemistry that happens here is with our enzyme that we call PEPCK. That's how we say that enzyme, okay? So 2 places that we see energy required. So we see ATP being required in the first step, and that's because that carbon dioxide loading actually requires some energy. And then we actually see GTP required in the PEPCK chemistry, and that's because it's actually providing that phosphate to do that phosphorylation chemistry. Okay, so a couple of things to highlight here. Pyruvate carboxylase is only found in the mitochondria. Okay? PEPCK is found in both the mitochondria and the cytosol. But remember, the rest of the gluconeogenesis enzymes, which are really glycolysis enzymes running in reverse, with the exception of G6Pase and FPPase, but all of those enzymes live in the cytosol. So to do gluconeogenesis, the first thing that we need to do is we need to dip into the mitochondria because pyruvate carboxylase only lives there. Then once we get to oxaloacetate, then we've got 3 choices. Okay, we're going to go through those choices on the next slide. One choice, because we don't have a transporter to get oxaloacetate directly out into the cytoplasm, the cytosol. So one option is we can take oxaloacetate and continue this chemistry in the mitochondria with PEPCK to make phosphenylpyruvate. There are transporters for phosphenylpyruvate. Or we can make oxaloacetate into malate. There are transporters for malate. Or we can make oxaloacetate into aspartate. There are transporters for aspartate. So the net equivalent here is making it into a molecule, making oxaloacetate into a molecule that there is a transporter for. So I know this next slide is going to look a little crazy, okay, so just bear with me for a second. So highlighting here that there are no transporters, okay, for oxaloacetate. So that's what we're saying here. There are no transporters for oxaloacetate. So if we look at oxaloacetate needing to get between mitochondrial and cytosolic compartments, you cannot transport that molecule directly itself, okay? Things that we do have transporters for. We do have transporters for pyruvate. So pyruvate can easily go back and forth between cytosol and mitochondria. So that one works okay. But what we're going to see here is that we are going to transport the net of oxaloacetate either as malate, because we're using the malate portion of this shuttle, as aspartate, because we're using the aspartate part of this shuttle, or another thing we can do is we can use PEPCK to make oxaloacetate into phosphenylpyruvate, and then we can do that there. So I'm going to add that to this slide because it's not specifically here, but we can take oxaloacetate and make it into phosphenylpyruvate using PEPCK. I'm spelling it like Pepsi. PEPCK, okay? So we're going to see this on the next slide. So options for things that we can do, and I'm going to highlight it here and then we'll see it on like another slide here. Remember, if we are talking about converting pyruvate, let's actually add this on here too. I think this will be helpful. Pyruvate going to oxaloacetate, okay? This happens with pyruvate carboxylase. This is only in the mitochondrion, okay? Now I can have oxaloacetate made into phosphenylpyruvate by PEPCK here in the cytosol, okay? So let's again think about how we're starting. We're starting out with pyruvate, and pyruvate has to be made into oxaloacetate. That's the first step of gluconeogenesis. The only arrow that I have for that is with pyruvate carboxylase that lives in the mitochondria. Okay, now once I get to oxaloacetate that's in the mitochondria, I can't get it out into the cytosol, but I have three things that I can do with it. The first thing is I can say, well, let me do my PEPCK chemistry here in the mitochondria because PEPCK lives there. I've got a phosphenyl transporter that lives in my inner mitochondrial membrane. So now I can get phosphenylpyruvate out into the cytosol. Rest of gluconeogenesis is easy. Okay. Another option is, you know what? I have two things that I can disguise oxaloacetate as that can allow it to get out of the mitochondrion. I can convert oxaloacetate into malate using malate dehydrogenase, use a malate transporter, get it out into the cytosol, use a cytosolic version of malate dehydrogenase to remake oxaloacetate, and then I can use the cytosolic form of PEPCK to make phosphenylpyruvate, and now I'm ready to do gluconeogenesis. One more, okay? Still having oxaloacetate in the mitochondrion here. Another option is I can use AAT, aspartate aminotransferase, to convert oxaloacetate into aspartate. I do have a transporter for aspartate. I can get that out into the cytosol, use a cytosolic version of AAT. Oddly enough, sometimes this enzyme is called GOT, so that gets confusing. Aspartate can be converted back into oxaloacetate, and then oxaloacetate to phosphenylpyruvate by that cytosolic version of PEPCK. Wow, that's a lot. I'm going to review it again on one last slide that hopefully shows those paths a little bit differently, maybe a little bit clearly. Okay, so we've got three paths for things that are going on here. So let me highlight some important things here. Remember that pyruvate carboxylase is only in the mitochondria. So this is a necessary step. So we must be in the mitochondria for pyruvate carboxylase chemistry. Okay, that's an absolute requirement. That enzyme only lives in the mitochondria. So depending on where pyruvate starts out as, there is a transporter. Remember we showed this, there is a transporter for pyruvate. So depending on where that is, it can get to where it needs to be in the mitochondria for pyruvate carboxylase to do its chemistry. Okay, now we highlighted once we're in the mitochondria as oxaloacetate, three options. Okay, so I'm going to start over here on the left, and I'm going to highlight that our first option is, we're going to call this the stay in the mito option, okay, which means we're going to do that pyruvate carboxylase chemistry and PEPCK chemistry all in the mitochondrion, okay? So we're going to stay in our mitochondria. So we're going to start with oxaloacetate, of course, in the mitochondria. And then we're going to stay in the mitochondrion. PEPCK, that mitochondrial version, is going to convert it into phosphenylpyruvate in the mitochondrion. Remembering, we do have that transporter for phosphenylpyruvate, so I can then take and use that phosphenylpyruvate transporter, get phosphenylpyruvate now out into the cytosol, and once I've got phosphenylpyruvate in the cytosol, then I'm ready to continue gluconeogenesis. So that's sort of like my all mito option. I stay in the mitochondrion as long as possible. Once you get to phosphenylpyruvate though, then you need to get out into the cytosol because that's where the rest of those gluconeogenic enzymes are. Again, reversing glycolysis enzymes. All right, we're going to call sort of our next one, use that malate shuttle. So we're going to call this a malate disguise. Malate disguise, okay? Obviously, we have to do our pyruvate carboxylase chemistry in the mitochondrion, but we're basically going to take and convert oxaloacetate into malate, and then we're going to use that malate shuttle. Okay, so this is going to be my malate disguise route. So again, once I've got oxaloacetate in the mitochondrion, okay, then I can use a mitochondrial isoform of malate dehydrogenase to make it into malate in the mitochondrion. Highlighting, coming back over here to this picture, we do have a transporter for malate. So malate can get out into the cytosol, and then once I've got malate in the cytosol, okay, there is a cytosolic version of PEPCK, so that's going to allow me to get to phosphenylpyruvate in the cytosol. I'm continuing this process. Okay, the last way that we can handle this, okay, is we're going to call this an aspartate disguise. So aspartate disguise. So we're going to take oxaloacetate and we're going to make it into aspartate. Okay, and then we're going to use the aspartate shuttle. Okay, so we're going to highlight this and make this yellow. Let's do that here. So the aspartate disguise. Okay, so this aspartate disguise is basically going to, again, we always start at the same point here. We're going to start with oxaloacetate. Let me make this a little bit darker here. I don't like, you can't see that too well. So the aspartate disguise here. So always have to start with oxaloacetate in the mitochondrion because pyruvate carboxylase lives in the mitochondria. So come over here, that enzyme AAT, I'm going to highlight that sometimes you see historical. This is called GOT. So if you see that, don't get confused. That makes aspartate in the mitochondria. We do have a transporter. Zipping back here for a second, we do have a transporter for aspartate. So now we're going to have aspartate that can go from the mitochondrion into the cytosol. And then we have a cytosolic version of AAT, which can make it back into oxaloacetate. And then once we've got oxaloacetate in the cytosol, that cytosolic version of PEPCK can convert it into phosphenylpyruvate. And now we're ready to go through gluconeogenesis by reversing glycolysis enzymes. Oh my gosh, I know that was a lot, but each one of these things highlights a different unique sort of story that we have about biochemistry. And we're using a specific sort of situation to highlight it. This story highlights the importance of there being key branch point metabolites that we don't have transporters for. So how do we remedy that? Well, we need to find alternative pathways, and often it's disguising it as another molecule. And in those cases, we have to make sure we also have cytosolic and mitochondrial versions of those enzymes to be able to reverse that disguise, either put it on or take it off to get back to that important branch point metabolite that we needed. Okay. We're going to revisit this malate aspartate shuttle in our citric acid cycle chapter because malate dehydrogenase is also an important citric acid cycle enzyme. And we're going to learn that malate dehydrogenase has a lot of different hats that it can wear, and depending on what it's doing is going to depend on who it's talking to in the cell.